A little bit more review of inverse trig functions, and then we're getting back into calculus. So first of all, we need to remember our definition for inverse functions. F composed of F inverse and F inverse composed of X of F of X. If they wind up just reducing down to X, then they are inverses of each other. Basically, you can think of this notation as being one thing undoes the other. Like x squared undoes square root, or squaring undoes square root, things like that. So for trig functions, we have to also consider our domain and range. Because of the fact that trig functions are periodic, meaning they're cyclical, which means they don't pass the horizontal line test, we have to restrict the domain, which subsequently restricts the range in our inverse functions. So we have to restrict our domain and our range for sine and arcsine. And if we do that, then we can have this situation. This is basically f composed of f inverse of x. Winds up being x. And f inverse composed of f of x winds up being x. It's the same idea. But the notation here says sine of arcsine x equals x. Arcsine of sine y equals y. So if I have a trig function, I can undo it by taking the arcsine of both sides of an equation. This is only true, though, if the domain is between -1 and +1, and the range is between -π/2 and π/2 in your inverse function. Same thing is true for tangent. We have -π/2 is less than y is less than π/2. And if that is the case for your range, then you can apply that property to both sides of an equation and wind up with tangent arctangent x is just x, or arctangent of tangent y is just y. And finally, the third one, actually there's 6, but I'm only giving you 3 because the other 3 that aren't on here are very, very similar to what you're seeing here. For secant, we have to be greater than 1, or let's see, and 0 is less than or equal to t is less than or equal to π/2, or π/2 is less than, this should be a y, by the way, is less than y is less than or equal to pi. The reason for that is if you go back and look at your graph of secant, you can see that the inverse of secant has a graph that's very weird. It's just like, bleh. And then there's another one up here. And the reason for that is, if I use this same little sketch right here, secant looks like this. And there's a void in between. Because of that void in between, when we go with inverse, we have to say that our range of values can't be within that void. So that's where this part right here is coming from. Why that or statement is there with those two different values. Anyway, if you've satisfied this and you've satisfied this, then you can apply your inverse function to both sides. The other 3 are similar, but the properties don't apply if the conditions are not met. So you have to meet those conditions. You got to think about them before you can apply them, and then you can apply them. So, arctangent of 2x minus 3 equals π/4. The question is, can we apply tangent to both sides to get rid of that arctangent? In order to do that, we got to look back and think about what our range of values for tangent is. So between -π/2 and π/2, which π/4 is between those values. So I'm looking at range because this is an answer. Answers are your range values. So our range is in the correct region, which means that I can take the tangent of both sides. And when I do that, the tangent of arctangent goes away, and I'm just left with 2x minus 3 equals tangent π/4. Well, the tangent of π/4, I can get off the unit circle, which is what? Tangent is sine over cosine, which is y over x. So root 2 over 2 divided by root 2 over 2, which is just 1. So really what I have here is 2x minus 3 equals 1. And now we're back in algebra 1. Solve for x. Add 3 to both sides. 2x equals 4. Divide both sides by 2. X equals 2. You missed algebra 1? Yeah. We've been doing algebra 1 all year. Okay, for the next one, we're given y equals arc sine x, where 0 is less than y is less than pi over 2. Does that fit with our range of values? Yeah, it does. So we're good. We can do this problem, which means that I can do what? Do I know how to work with arcsine? Really? Oh, yeah, that's what I'm talking about. We don't want to have arcsine, we want to have sine. So we're going to apply sine to both sides, and we wind up with sine y equals x. Okay, now we're supposed to find cosine y. There's no cosine involved on this problem. So that means we're going to have to go back into our deepest and darkest depths of memories to recall what we did in trigonometry. By memory, I mean memory, not note cards. No. What do sine and cosine go with? Okay, tangent. But what do those three things apply to? Like, when do we use them? What kind of triangles? Right triangles. So we're going to set up a right triangle here. Yes, yes. Set up a right triangle. Now we're given that the sine of y is equal to x. That's kind of like saying the sine of y is equal to x over 1. Trig functions deal with ratios, right? So sine is what? SOHCAHTOA, so opposite over hypotenuse. So our angle that we're looking at right here is angle y, right? Sine y, or sine theta. So then opposite over hypotenuse. Opposite is there. So that's my x, and then my hypotenuse here is 1. Now, I don't know this side. We can find it because it's a right triangle. How am I going to find this, considering it's a right triangle?
1 squared minus
the Pythagorean theorem, yeah. So it's going to be 1 squared equals x squared plus whatever you want to call this. A or b, because the Pythagorean theorem is a squared plus b squared is c squared. B, okay. So then that's plus b squared. We want to solve for b, so we're going to subtract x squared from both sides. 1 squared is just 1, and then we're going to take the square root of both sides. So we have 1 minus x squared equals b squared. And then I square root both sides, and I have the square root of 1 minus x squared equals b. Normally plus or minus, but since we're dealing with dimensions, just positive. So b is actually the square root of 1 minus x squared. Now we can answer the problem. The problem says find cosine y. Well, cosine is what? Adjacent over hypotenuse. So that means that cosine y equals the square root of 1 minus x squared divided by the hypotenuse, which is 1. So divided by 1, which I don't have to write. So that's my answer. Draw a triangle. It's going to help. It will also help on this one. Enjoy. And then we'll talk about it. So how are we going to set that up? All right, apply secant to both sides. Oh, that's arc secant. So now we have secant y equals square root of 5 over 2. Now what? Okay, set up a triangle. And when you're doing this, by the way, you can set it up so that the quadrant that it's set up in is correct. Like if you consider this to be the origin, you can draw your triangle this way, or you can draw it down in the third quadrant or in the fourth quadrant based on the angle that you're dealing with. Like in this one right here, 0 is less than y is less than pi over 2. That's between 0 and 90 degrees. So setting it up like this was correct. Remember that your hypotenuse will never be negative, but when you start dealing with coordinates on a coordinate plane, then this length can have a negative sign on it, and so can this one. But if you keep your hypotenuse positive, that will help you with what the signs of these things are going to wind up being. If you remember that from pre-calculus. You should. Anyway, we're going to put our y right here. This is my right angle, because it looks like one. And then what? Secant is the reciprocal of which? Cosine. And cosine is adjacent over hypotenuse. So that means that secant is hypotenuse over adjacent. So what's going to go here? Square root of 5 and then 2 here. All right, so all we got to do is figure out this side using the Pythagorean theorem. What do we write? Square root of 5 squared equals. You can call it b, you can call it a. I feel like drawing an a, so I'm going to write a squared. So that gives me what here? 5 equals 4 plus a squared. Subtract. 1 equals a squared. Square root both sides. 1 equals a. So a equals 1. Now we need tangent y, so that is what? Opposite over adjacent. So that is 1 divided by 2. 1/2. There's your answer. Here is a lovely list that you need to memorize. And by memorize, I mean memorize. Commit it to memory. You have to know it. You have to know these by heart. What I'm saying is you need to have it memorized. Because I'm not going to give you a note card. All right, the derivatives of your inverse trig functions are all listed here. When we learned about the derivative of the natural log of x, I never said it, but you may have put it together. We found out that the derivative of the natural log, which is not your normal polynomial type function, it's a transcendental function. That's what that word kind of means. We found out that the derivative was algebraic, meaning kind of like a polynomial. Not transcendental. The same thing is true for your inverse trig functions. When you take their derivatives, you wind up with something algebraic. The trig function goes away. So it's kind of an interesting thing. Now, the other thing that I want to point out here is, yes, there are 6 of them, but really, you only need to memorize 3. Nope, sine, tangent, and secant. The cos are all very similar. The only difference between sine and the cosine is what? The negative sign right here. The stuff is all the same. The only difference between tangent and the cotangent is what? The negative sign. And the only difference between secant and cosecant is the negative sign. All of them have u prime in the numerator. The cos are all negatives. So then it's just a matter of remembering what the denominator for each is. For arcsine, the square root of 1 minus u squared. For arctangent, 1 plus u squared, not square rooted. And then for secant, the absolute value of u times the square root of u squared minus 1. So those are the 3 things you really got to focus on. The rest is patterns. The numerator is always u prime. The cos, the numerator is actually going to be negative. Somebody with more time on their hands than Facebook allows these days. All right, so let's use those derivatives and find those derivative rules and find the derivatives of these four things here. We're taking the derivative of the arcsine of 2x. So yeah, u is going to be 2x, so the numerator will be what? 2. And the denominator will be, I'm going to write that down, u equals 2x. This one has a square root, okay. Then what? 1 minus u squared. So it's 2x squared, which is 4x squared. That's your derivative. You're done. All right, the next one. Okay, and we're using arctangent this time. U prime on top divided by 1 plus 9x squared, u squared. And that's your derivative. Okay, the next one, arcsine square root x. Okay, so x to the 1/2. It might be smart to write down u prime in this one. U prime is okay. Oh, now. U prime is this, and I'll go ahead and write it up top, even though we know we're going to have to do some simplifying with that negative exponent. Square root of 1 minus u squared, but the square root of x squared is just x. So we have 1 minus x underneath the root. Okay, so this guy definitely goes to the denominator, but what do I do with this 1/2? The 2 also winds up down. So what's in the numerator here? Just 1. Over
2 square root x square root.
Okay, now can that be simplified? Yes. If I multiply radicals with like indexes or indices, then you can multiply the stuff inside. Remember that? It's like if I have the square root of 2 times the square root of 3, I get the square root of 6. Right? So I can do the same thing here, and when I do, I have 1 over 2 square root x minus x squared. There's your derivative. So it's not too bad. You just got to remember how to take the derivative in the first place and then simplify it using your regular algebra. What do we do on this one? Okay. Now what? 2e to the 2x. Okay. Dealing with secant here, arc secant. So u prime on top, 2e 2x. Divided by absolute value of u is e to the 2x. Okay, so secant was what? U squared minus 1. So we have e to the 2x squared. All right, I'm going to write it down. E to the 2x, I see where you're going with that, squared. But I'm going to write it down so we see it. That's u squared. And then what else? Minus 1, okay. Now we got to simplify that, obviously. And you were trying to go power to a power. We're going to multiply. What about this? Why not? So what? Think about it. If I raise e to a negative number, what happens? It's still positive. So this is never going to be negative. In this case, because of the fact that this is e to the 2x, this situation is never going to actually be negative, ever. So therefore, I didn't need the absolute value symbol here, which means that I actually can let those go away. So then we just need to simplify that right there. So we get, what? And there's your answer. Take the derivative. Before we do, what do you see? Several different things we're going to have to do. This term is going to be what? We got a thing for it, okay. This term, how am I going to take that derivative? Product rule. And then when I get to this part, chain rule. Okay, or general power rule. Good. So let's go ahead and start taking the derivative. U prime, which is 1 in this case, over 1 minus x squared. The u squared was just x, so it becomes x squared. Good, this one's done. Okay, product rule. So that would be g prime f, right? Which, so I'm going to write down that f now. One minus x squared to the 1/2 if I rewrite that. The 1/2 comes down. 1 minus x squared. We're taking the derivative, so we're subtracting 1 from the exponent. Times the derivative of what's inside, negative 2x. Is that it? Okay. That's the calculus. Now we use algebra to simplify this. 1/2 and negative 2. Right. What about this x? Okay, so I'm going to rewrite this now. 1 over the square root of 1 minus x squared plus the square root of 1 minus x squared. What? Minus times 1 minus x squared to the negative 1/2.
Okay. So,
Common denominator.
which that already, it has a common denominator.
Which one?
Negative 1.
This one.
If you rewrite it.
Because this is actually minus x squared over 1 minus x squared square rooted.
The only thing we need to get a common denominator is that one.
This middle guy needs a common denominator.
Which is, so times
What is the common denominator?
square root of 1 minus x squared.
But that means I need to multiply that on top as well. So the square root part disappears. Combine everything, okay. Y prime equals.
1 plus 1.
How about 1 minus x squared in the denominator?
We got 1 plus 1 minus x squared minus x squared. All that equals 2 minus 2x squared.
2 minus 2x squared over the square root of 1 minus x squared. Are we done? We can take the 2 out. We will, because there's actually more to do here. We take the 2 out, and we have 1 minus x squared divided by, technically not the square root of 1 minus x squared, but 1 minus x squared to the 1/2. Yes. These are like bases here. When you have like bases and you're dividing, you subtract the exponents. That would be to the first power. Divided by that to the 1/2 power, subtract 1 minus 1/2 is 1/2. So I wind up with 2 times the base, which was 1 minus x squared to the 1/2, which I then can rewrite as 2 square root 1 minus x squared. There's your answer. Now, the little note down here, the interesting thing about what just happened is the implication for integrating some algebraic functions. What do you notice? So by integrating some algebraic functions, I mean, take a look at the answer and look what got us that answer. If we're integrating, we're going the other way, right? So if I give you a problem that looks like this, what do you notice about what the answer could potentially look like? It could have a trig function in the answer. Yeah. We actually discovered there was a homework problem one time, a while ago, that had a trig function in its answer. That was a mistake on the book's part because technically that hadn't been taught yet. But they were right because they just integrated it using an integration property that we're about to learn. Yeah, so it's kind of an interesting thing. We start with algebraic, we wind up transcendental. Or we can start off transcendental and wind up algebraic. You've now learned all 24 of the basic rules of differentiation that we study in this course. Take a look at those 24 rules on the inside cover of your book. All 24 of them you know. And it is expected that you know these rules by heart and can easily use them on the AP exam. All 24 of them are tested on the exam in some way.